All right, today we're going to look at the double angle and power reducing formulas. The double angle formulas are easily developed using the sum formulas that you already know. So let's just refresh our memory on the sum formulas, and let's take a look at the proof of the cosine of 2x. So for the cosine of 2x here, we can think about the cosine of x plus x, and then we know that the cosine of x plus x can equal the cosine sum formula. And so that is going to be the cosine of x times the cosine of x minus the sine of x times the sine of x. And then simplifying each side of this, I know that this statement is true because of the cosine sum formula. The left side now becomes the cosine of 2x. There's our double angle. And the right side can become the cosine squared of x minus the sine squared of x. Now, you may recall that this is one of the cosine double angle formulas. You might also see the cosine double angle formula written in a couple different ways. You can rewrite the cosine double angle formula by doing a simple substitution using the Pythagorean identity. So we can say that the cosine of 2x is also equal to, I can put the cosine squared of x minus, and then instead of sine squared, I can write it as 1 minus cosine squared of x using a manipulation of the Pythagorean identity. And then I get the cosine squared of x minus 1 plus the cosine squared of x is equal to the cosine of 2x. And then I can simplify that to see that the double angle formula for cosine can also be written as 2 cosine squared of x minus 1. Similarly, I can do the same thing to write this in terms of a sine function. And I can say, go back to my original here, and I can say that the cosine of 2x is equal to, and instead of substituting my sine squared, I'm going to substitute my cosine squared is going to be 1 minus sine squared of x using the Pythagorean identity, and then minus a sine squared of x. And so simplifying this, I get the cosine of 2x is equal to 1 minus 2 sine squared of x. And now I can see the cosine double angle formula written in 3 different ways. You can review the sine double angle formula and the tangent double angle formula proofs in your textbook, or you can try them out for yourself. And here you can see the 3 formulas on the screen. And again, you can prove those on your own for the other 2. Now let's take a look at an example. So using the double angle formulas, we can find the exact value of sine of 2u and tangent of 2u given the cotangent here is equal to -5 and that u is restricted to 3 pi over 2 to 2 pi. So the first thing that I would want to do is I would want to draw my angle. So I have it drawn in the correct quadrant. So 3 pi over 2 to 2 pi, I know that that is going to be in quadrant 4. So here I'm going to draw my x and y axes, and I'm going to draw a triangle in quadrant 4. Draw it anywhere in quadrant 4, doesn't matter. And so this is here my angle u, okay? And that's just from this restriction. And then I want to find the sine of 2u and the tangent of 2u. So let's just start by thinking about the formula for the sine of 2u. So that formula for the sine of 2u, I can write as the sine of 2u is equal to 2 sine of u times the cosine of u. And so what I need to do is I need to figure out the sine and the cosine, not of 2u, but just of u, which is what my diagram represents. So I also know that the cotangent of u is -5. So I can think of this as the cotangent of u is -5 over 1. Since cotangent is the reciprocal of tangent, I know that tangent from SOHCAHTOA is opposite over adjacent, so that means that cotangent is going to be adjacent over opposite. So my adjacent side, I'm going to put in a 5, and my opposite side, I'm going to put a 1. Since I'm in quadrant 4, I know that the 1 is going to be my negative, and 5 is going to be my positive. So since I have to do sine and cosine, I will need the hypotenuse, so I can use my Pythagorean theorem. as negative 1 squared plus 5 squared is equal to, let's call this a squared. So that means that a is equal to, and we're going to just do the positive square root of 1 squared is 1 plus 5 squared is 25. So add those together, we get 26. So we get the square root of 26. And we can't simplify the square root of 26. So we're just going to leave this here as the square root of 26. And so now I can find the sine and the cosine as needed. So 2 times the sine of u is opposite over hypotenuse. So negative 1 over the square root of 26. And I'll rationalize at the end if I need to. Sometimes it rationalizes within the problem. The cosine is adjacent over hypotenuse, so it's going to be 5 over the square root of 26. And we can see here that this will rationalize itself out. So this means then that the sine of 2u is going to equal, my square root of 26 are going to rationalize and going to give me negative 10 over 26, and I can reduce that. So the sine of 2u is equal to negative 5 over 13. All right, so there's sine of 2u. And now I can take a look at tangent of 2u. Again, we will start with the formula for the tangent of 2u. Give myself a little more space here. So I can say that the tangent of 2u is equal to 2 tangent of u all over 1 minus tangent squared of u. And here, I don't need my hypotenuse, so I'm just going to get 2 times the tangent of u. Well, we know that that's also the reciprocal of cotangent, so it's going to be negative 1/5. We can also see on the diagram that the opposite divided by the adjacent is also negative 1/5. And so then I have negative 1/5 quantity squared. And then I can go ahead and I can simplify this. And so I get the tangent of 2u. Be careful with your fractions within fractions. I get negative 2/5 all over. And then I have 1 minus negative 1/5 squared is going to be 1/25. So 1 minus 1 over 25. Let me just move up here. So now I have that the tangent of 2u is equal to negative 2/5 over 24/25. And simplifying this, I'm going to get multiplying by my reciprocal. And you don't need to show this work, but I'm just going to show it so people can follow along. And then I'm going to go ahead and I'm going to simplify. So here we have reduced by 5, a 1 and a 5, reduced by 2, a 1 and a 12. And I'm going to get that the tangent of 2u is equal to negative 5 over 12. And there we go. We have our tangent of 2u and our sine of 2u. All right, let's continue on with solving an equation. So here we're solving 2 sine of x plus sine of 2x. There's no domain restriction, so we're solving it over all reals. So when I'm looking at this here, what I want to notice is I want to notice that this is an x and this is a 2x. So in order to use any of the simplifying properties that we've already learned, we want to make sure that we have the same argument in there. So I'm going to expand my sine of 2x using the double angle formula. So 2 sine of x plus the sine of 2x is 2 sine x cosine of x, and then that's equal to 0. And so now I can see that I can factor out the 2 sine of x from each of my terms. And when I do that, then I am left with 1 plus cosine of x is equal to 0. And so now since I have this equal to 0, I can use my zero product property and break it up into 2 parts. 2 sine of x equals 0, or 1 plus the cosine of x is equal to 0, and solve each of these equations independently. So go ahead and solve each of those equations independently and pause the video. All right, and then we can see that we end up with x equals k pi for the sine equation and x equals pi plus 2k pi for the cosine equation. And k is an element of z, so I'm going to combine these into one set notation, x such that x is equal to, would just be k pi, and k is an element of z. And these overlap each other, so we don't need to have both formulas, we just have the one formula. All right, let's take a look at the next example. So you might be faced with graphing something that you've not seen before, and you can use the double angle formulas to help you graph this so that you can put it into a form that you know how to graph. So looking at this problem here, I'm thinking about the double angle formulas and what I can do with those double angle formulas. So what I could do is I could factor out the 3 from both terms, and then I'm left with a double angle formula. So go ahead and factor that out, and can you see the double angle formula that remains? Do you see this quantity of 1 minus 2 sine squared of x is the same as the cosine double angle formula? So it's 3 times the cosine of 2x. And now we can look at that, and we already know how to graph that. That is simply a cosine function with a vertical stretch of 3 and a period change of 2. So graphing this equation, I can go to my graph. I know that my period is going to be pi. Okay, so my cosine graph and my amplitude is going to be 3. I don't have a phase shift, so I'm going to start here at 3, also no reflections, and then end my period at pi, so there's 3. I know that halfway between there I'm going to be at -3, and then halfway between each of those halves I'm going to be at pi over 4 and 3 pi over 4, 0. So graphing this here is 1 period from 0 to pi. It asked me to graph from 0 to 2 pi, so I'll just continue this, and I will have my function from 0 to 2 pi. And so now I'm able to graph this function that has a sine squared in it without knowing a parent function for sine squared by changing it and converting it into a function that I know. Pretty cool. Let's check out another way that this double angle formula can be helpful. So here this says to write as an algebraic expression, and we have the sine of 2 arc cosine of x. Now we've done problems similar to this already, so let's do it in the same way. The first thing I want to do is I'm going to draw a diagram. A diagram is going to go a long way with this problem. And like we've said before, whenever we have algebraic expressions like this, we're going to draw them in quadrant 1. So here I'm going to draw a triangle in quadrant 1. And when I read this quantity here, this arc cosine of x, this represents an angle. So I'm going to just say, let's let theta equal arc cosine of x. Well, if theta is arc cosine of x, then I know that the cosine of theta is equal to x. And I can think of x as a fraction as x over 1. So on my diagram, I can label theta here, call this theta, and then the cosine of theta is x over 1, so that's going to be adjacent over hypotenuse. And so I have 2 of the sides of my triangle. Now, if I think about what I'm trying to find the sine of 2 arc cosine of x. So this is going to then be equal to the sine of 2, and if I substitute my arc cosine of x is theta, it's simply the sine of 2 theta. And I know the formula for the sine of 2 theta. So the sine of 2 theta is going to be 2 sine of theta cosine of theta. And now I just need to use my diagram to find this. Well, in order to find sine, I do need to find the opposite side. So let's call the opposite side a. So I know that x squared plus a squared is equal to 1 squared. So then I know that a is going to be the positive value of the square root. So just positive square root of 1 minus x squared. And so now I can substitute for the sine and for the cosine using my diagram. So I get 2 times the sine is the opposite, which is the square root of 1 minus x squared over the hypotenuse, which is 1, and then times the cosine, and the cosine is adjacent, which is x, over hypotenuse, which is also 1. And then I can just simplify, and so I have 2 x square root of 1 minus x squared. And this is my sine of 2 arc cosine of x. So we did problems like this in a previous chapter with our inverses. So this is now just the same idea, but now we have a double angle formula that we're using as well. All right, let's take a look at another way we can use these double angle formulas. These double angle formulas can be used to derive a whole new set of formulas, which are called the power reducing formulas. Now, again, I want to draw attention to the fact that these formulas are all connected. So if you know some of the formulas, you can usually figure out the ones that you may have forgotten, or you focus on a certain few to remember, and then you can derive the other ones as needed when you're working on different problems. So here, if you're asked to graph something like this, 2 cosine squared of x, you can use strategies that we've already talked about, or you can use a power reducing formula to reduce this cosine squared into something that you are able to graph, that you know how to graph. Okay? So these are derived, again, from the double angle formulas. So here we're going to look for how to get rid of this cosine squared. So I'm going to think of a double angle formula that has cosine squared in it. The one I'm going to use the cosine double angle formula. So cosine of 2, and I'm going to use 2u since that's what the text uses. So cosine of 2u, and I'm going to write this one using just the cosine squared manipulation of the formula. So it's going to be 2 cosine squared of u minus 1. And all I'm going to do is solve this for the cosine squared of u. So I'm going to add 1. So I'm going to get cosine of 2u plus 1 is equal to 2 cosine squared of u, and then divide by 2. So cosine squared of u is equal to cosine of 2u plus 1, all divided by 2. And this is the power reducing formula for cosine. Pretty simple. Similarly, we can do the same thing for the sine. But for the sine, we're going to start with the cosine double angle formula that uses a sine squared. So think about what that formula is and go ahead and write it down. What you should have written down is 1 minus 2 sine squared of u. And now just manipulate it until you isolate sine squared of u. All right, with manipulation, did you end up with the sine squared of u is equal to 1 minus cosine of 2u all over 2. And notice on this previous step, let me rebox that answer for you. On this previous step here, I was dividing by a negative 2, and so then I just distributed that negative into my numerator to get 1 minus cosine of 2u. All right, then for the tangent of 2u, you can simply do the sine divided by cosine. So tangent of 2u can be the sine of 2u divided by the cosine of 2u. And you have both of those formulas already. And so I have 1 minus the cosine of 2u divided by 2, all divided by, and I'm going to write this one as 1 plus the cosine of 2u divided by 2, right? Because cosine of 2u plus 1 is the same as 1 plus cosine 2u. And then I can cancel out my 2's, and then I can see that the tangent of 2u is equal to 1 minus the cosine of 2u, all divided by 1 plus the cosine of 2u. All right, very good. So now we have a whole nother set of formulas. And again, understanding how these connect to each other is really helpful to help you remember the formulas that you need to use. Okay, now let's get back to completing that graph. So we have f of x is equal to 2 times the cosine squared of x. So let's do a substitution that we know for the cosine squared of x that we just derived. So our f of x is equal to 2 times, and now we're just going to substitute in that cosine squared of u. But now here we have x, so we have 1 plus the cosine of 2x all over 2. So I just did that substitution here for cosine squared of x. And then I can simplify, I can cancel out my 2's. And I'm going to rearrange this so that it's in the format that I know for my parent function. It's the cosine of 2x and then plus 1. And notice there are no parentheses around this. This plus 1 is outside. So the only thing that's inside with the cosine is the 2x. So this plus 1 is a vertical shift of up 1 unit. And this is your b value. And so that means that the period is going to be 2 pi over that b value and the absolute value of that. So our period is going to be pi. So we have a period of pi, so that's our period change. And then we have a vertical shift of up 1 unit. So that vertical shift up 1 unit means my midline is going to be here at 1. You don't need to draw the midline in. I like to because then it's a little bit easier for me to see that I made the graph correct. And then I'm going to graph my cosine function. So my a value is simply 1. So I'm just going to be up 1 from that midline. And then my period is pi, so I know that my second maximum is going to be up there at pi, comma 2. And then halfway between, I know I'm at 0, and halfway between I'm at pi over 4, and then 3 pi over 4 on that midline. So here is one period. And then it says to graph on the interval 0 to 2 pi, so I'm going to repeat for one more period. And then I'm going to have graphed from 0 to 2 pi. All right, very good. And so now we can graph this cosine squared function by using what we know about the power reducing formula and our other cosine functions already.